Welcome everyone. This is Greg Sitton, and he is from Gusmer. He is has been in the wine industry and for a long time, and he's going to talk to us about filtration. I'll let him introduce himself a little bit and give you a little background. But thank you guys for coming.
Yeah, good morning. As Sarah said, my name's Greg Sitton. Been with Gusmer Enterprises for 8.5 years now. Been in the wine industry for almost 20. Different supplier side jobs, so I was in different cooperages and cork closures before that. So been around the industry a long time, and we supply you guys with some membrane filters for your bottling line here. So that's the main purpose of the conversation today. Gusmer also gets into a lot of things related to fermentation, filtration, some equipment, some lab stuff as well. So pretty much anything to do with fermentation and filtration. And I have cards up here if anybody wants one for future contact. But we're here to talk about wine filtration, in particular sterile and membrane filtration. So are all you guys on the bottling side or QC side? Bottling? QC. Bottling. Okay, a little bit of both. I'll try to touch on both sides of that as I go through these slides. Please ask questions along the way. It's better if this works as a conversation more than just me explaining things to you or trying to explain things just through slides. We'll get into it right away. We're going to go through, an introduction to sterile filtration. Why do we sterile filter? Factors for aseptic or membrane filtration, the types of filters that you might see, membrane cartridges themselves, how they're manufactured, the installation and operation and sanitation of them, and then integrity testing, which is one of the most critical points in operation to verify that you have sterility. So why do we sterile filter? Basically, we're looking to remove yeast and bacteria so that that package, that product that you put in package, stays that way. There's a lot of work that's done over on the seller side to make sure that things are stable with cold stability, making sure that the wine is not going to change in package. But if you have yeast in there and the presence of sugar, it's going to change. And if you have bacteria in there, you can actually create some health issues potentially. So the last step in filtration on the bottling line, sterile filtration, is to remove that yeast and bacteria that could possibly change the perception that the customer has of that product or cause health problems or exploding bottles on the shelf, which you don't want. So we're trying to remove microorganisms mostly. Sterile filtration or membrane filtration is just one step in the chain. I like to look at the winemaking process from when you receive the grapes at harvest all the way through to the bottling line as different steps in clarity, different steps in filtration along the way. Whether you're settling in tank and racking off of that or using fining agents that then pull those things to the bottom and pulling the clean wine off the top, or running through crossflow or a plate and frame filter. That's all part of the process. This is sort of the last step when we talk about sterile filtration, making sure that it's stable going into package.
What are some of the things that can cause, and you may touch on this already, but what are some of the things that can cause filtration issues once you get to aseptic?
There's a whole lot of them, and I'll touch on some of these things, but generally anything that you're adding to the wine, the grapes and seeds and stems themselves, they have certain properties that can make filtration difficult, like pectins. So you can get pectins that will gum up your filters and cause you trouble on the bottling line, and you're getting, a few 100,000 gallons maybe through a 12-round housing as opposed to like running clean for a long period of time. Additives like concentrates, Sugars can also be challenging as well. Those are probably, the colloids in general are the most challenging. Proteins, things like that. Soft particles, anything that's soft is going to be really challenging on a filter, whether that's a depth filter or a membrane filter. But the membrane filters, and I'll touch on it in a little bit, membrane filters are expensive in comparison. So any work that they can do on the cellar side and pass you a clean wine is going to be advantageous and less expensive. And that's the critical factor. So if you're fining in tank with bentonite, for example, bentonite is pretty cheap in comparison to a final filter. You can treat thousands of gallons in a tank and get a level of clarity. That's one step. Then you go on to another step like crossflow that's going to remove more particles, and then finally on to sterile wine filtration. Did that answer the questions? Kind of. So ultimately, membrane is kind of the last step. These are points of contamination or potential points of contamination. You know, you have the beverage itself, you've got plumbing, you've got containers themselves that can have contamination already in them. Yeast is already everywhere. Bacteria is everywhere. The filler bowl, that's why we do all of the cleaning operations that we do to make sure that we have as sterile as possible situation that we're running into. Human hair, you know, contamination from the operators, things along those lines. Those are all points of contamination or potential points of contamination. Cleaning may remove a large number of yeast and bacteria. A dirty surface might have 10 million bacteria per square centimeter. A clean surface might have 10,000 bacteria per square centimeter. And a disinfected surface may have 10 living bacteria per centimeter. This is all the scary stuff to me. Like, I don't know how microbiologists live in this world, you know, knowing what they know. Because this, you know, it's everywhere. And you can't really effectively kill all of it. So we have to do certain things to make sure that we're controlling it and limiting it as best we can. Cleaning and disinfection routine does not necessarily kill all microorganisms, but it reduces their numbers to acceptable levels. In the presence of alcohol, for example, bacteria doesn't really thrive. Yeast depends on certain situations. So we're taking that load of bacteria and yeast and reducing it to an acceptable level that's not going to thrive in alcoholic conditions in package. Microbes reproduce by splitting in two, and under ideal conditions, bacteria divide in two every 10 minutes. That's the really scary part, right? So one bacteria cell can become 1 million in 3 hours and 20 minutes. So that's in ideal conditions. Wine, as I've already mentioned, is not ideal conditions in the presence of alcohol and pH and all of that. It's probably going to happen much slower. However, it's important to know that we need to control all of those microorganisms as best we can throughout the process. So we monitor yeast and bacteria populations that are entering the process, during the process, and in the finished product up to point of use. We do our best to control or eliminate undesirable populations to minimize risk. This is what you guys do in QC, right? Pull samples, plate them, incubate them, do cell counts, all of that kind of stuff, just to verify, did we get package in the bottle in the way that we wanted it, and that it's not going to create a problem down the road. Any questions up to this point? A membrane filter is considered a surface media. It's very thin. It's a polymeric film with a controlled porosity. So it's only 0.1 millimeter thick. It's very thin. Typical materials that it's made of is nylon, cellulose esters, polyester, or polyester sulfone, or PES. You guys typically are using PES in your final membranes here. That typically is, like I said, 0.1 millimeter thick, so very thin, and has controlled porosity. Because it's so thin, it's vulnerable to plugging or blinding off that membrane surface. I like to equate it to like if you're trying to get water through a piece of paper, right? Versus a sponge. So the media that they use on the seller side, the filter sheets that they use on the seller side pre-bottling are much thicker and can hold a lot more dirt, call it dirt loading capacity. These membranes don't have a lot of dirt loading capacity because they're very thin. So you pretty much get what's on the surface, and you don't have the ability to build up a lot of particles. So we want to make sure that we protect that as much as possible. Common pore size ratings are 0.2, usually used for water filtration, 0.45 micron, which is considered sterile in the presence of alcohol, and 0.6 is usually for a pre-filter protecting that final filter, and then 1 micron is sometimes used in, and there are definitely others up to like maybe 15 micron that are available, but not nearly as common use as in sterile filtration with the 0.6 and the 0.45. Ratings are established according to the membrane's microbial retention pore performance and not its actual physical pore size. So a 0.45 membrane will quantitatively retain a particle that is 0.45 micron. Quantitatively is 10 to the 7th or 99.979% reduction in the number of microbes downstream. In the case of bacteria, 1 out of approximately 10 million cells could possibly get through. But like we talked about, wine is not an ideal condition for those cells to thrive, so we consider that sterile. To be truly sterile in non-alcohol or non-presence of alcohol, you would need to be at 0.2. Membranes are expensive when they plug prematurely, but inexpensive when they achieve their full life. So a membrane filter, you know, looks like this, 30 inches long, costs around $300. It's pretty expensive when you add 24 of them into a housing or 12 of them into a housing. It adds up really quickly. So you want to do what you can to protect those, right? And make sure that you're getting as much throughput as you possibly can. And we do a lot of work to try to gain throughput and make sure that we're pushing that limit as far out as we possibly can. One of those filters could filter up to 100,000 gallons of wine. That's kind of a benchmark, 100,000 gallons per stick, or 1.2 million through a 12-round housing. And your cost goes down significantly, so it becomes almost negligible. It becomes 0.3 cents per gallon from that $300 investment, right? If you're getting that throughput, and that's really the critical part, is making sure that we get that throughput, because otherwise you plug right away, you got dirty wine coming in from the cellar side, it didn't pass filterability, you try to run it through these filters, and you just plugged $5,000 worth of filters about that quick. So it's important to always keep an eye on throughputs and filterabilities and wines that are coming in from cellar, so that the bottling line is set up for success, because these are very expensive when they do go down. And then Sarah calls me and I come down here and I'm like, I don't know, it was dirty wine. Yeah, anyway, anybody have that experience where it plugs right away and like, yeah.
Change them out.
Yeah.
Yep.
That's a sad day when that happens.
It is. It is. A lot of time wasted.
You know, it's oftentimes in wineries of this size, and Delicado seems to do a very good job of this, but it has to be a team approach. It can't be a silo approach. Like the seller has to be passing you wine that is clean, and it has to be moved through the pre-bottling tanks fairly quickly, and we'll get into some of those reasons. But it can't just be like seller is done with it and you know what, it's bottling's problem now and I'm gonna walk away from it. It's gotta be like a full team approach, kind of top-down view, and I know you guys spend a lot of time meeting with different teams to make sure that that is happening. Because a lot of times that's what happens. In those cases, it's a lot less expensive if the wine is passed back to the seller because their filtration methods are a lot less expensive. So if it's possible to pass it back to them and rework it so that it comes back cleaner, it's a lot more cost effective. So it's just a matter of where you place that cost in filtration.
How often do you see people check like filterability?
It's more common than not. Most small wineries may not know a lot about filterability or have the ability to check it. Large wineries are almost always using a filterability, either the Bolton method or Jukless method for testing filterability. Where we run into problems is tank residency time and how long it's sitting in tank. Maybe you checked filterability when they passed it to tank and it sat there for a week or maybe even 2 weeks. And filterability was not run again before passing it from pre-bottling tank into the bottling line. That's usually where the problem occurs, is where are you checking filterability and how close is it to bottling, and then do you have a method or a protocol for dealing with a wine that doesn't pass filterability? Does it get passed back to cellar? Do you have a lenticular you can run it through? How big is that lot? There's a lot of different questions. Where is it going? You know, those types of things. But that becomes very critical in management of your throughput in the whole process. Tank residency time, if you're not familiar, cellar will pass the wine to a pre-bottling tank, and if it stays in that tank, I should mention, by the way, my daughter painted my nails. I didn't even think about it, but my daughter painted my nails, so don't be distracted by my femininity here, I guess. I identify as he, him. Anyway, tank residency time. So once that wine is filtered on the cellar side and then gets passed to these pre-bottling tanks, some of those molecules start to recombine. And so filterability changes on a daily basis, even an hourly basis. So if you're checking filterability on the way in, but it sits there for a week, you have a lot of change that's taking place, and it can foul up those filters quicker than we'd like. So you want to make sure that filterabilities ideally are done close to bottling, and your tank residency time is as little as possible, as reasonably possible. That's hard sometimes. So here's a little bit more about what happens on the cellar side, properly preparing the wine for membrane filtration. It can include a tight filter pad, which is what you guys use here typically, is like a 0.2 or a 0.4 filter on the filter press behind the bottling line over here. That's usually the last step, as I know it, at least in your process before going into bottling. Sometimes it may come off of crossflow and go directly into those tanks. Crossflow is typically a 0.2 micron. And you would think that a 0.2 micron to a 0.6 micron to a 0.45, because you've got 0.2 on the crossflow, 0.2 on the pad filter, then you go into your bottling tank, your pre-bottling tank, then you go to 0.6 on your pre-filters and 0.45 on your final filters. That's a lot of filtration, and it seems like a lot of redundancy. And you would think that 0.2 to 0.6, you'd be filtering nothing. But what happens in that pre-bottling tank in recombining molecules becomes critical. And not all particles filter the same. Hard particles are relatively easy to filter, soft particles are more difficult. So colloids, your proteins, pectins, things along those lines are much more difficult. They flatten on the surface and reduce your surface area on that filter. Filterability testing the wine prior to membrane filtration becomes really critical. We've kind of covered all of this already. Cartridge pre-filter of slightly larger pore size is used in line for protection. That's your 0.6 pre-filters. If you look at any of these lines, they're going to have 2 cans. Sometimes, well, you guys don't have the redundant lines here, but 2 cans. One is your pre-filter, one is your final filter. The pre's are 0.6, the finals are 0.45. The pre's are only there to protect that more expensive final filter. Rule of thumb on sizing membrane filtration is about 9 to 12 gallons per minute per 30-inch cartridge. This becomes important when you're talking about your filler bowl. You size that can with number of filters in it to make sure that you are keeping that filler bowl full or full enough to keep up with your line, right? So faster lines need bigger cans. Slower lines can use smaller cans. If you're a home winemaker or a small operation, you might get away with a single round, maybe even a 10-inch cartridge instead of a 30-inch cartridge. But the critical part about sizing is making sure that you keep up with your filler bowl. So on a 12-round housing, 108 to 144 gallons per minute, and your pre-filter suggested flow rates at 9 to 12 gallons per minute per 30-inch cartridge, so it's the same. Any questions so far? Am I boring you guys or telling you everything you already know? So this is what it looks like on the line. Typically, you've got, your pre-filter 0.6 micron and your 0.45 final filter. That's what it would look like on the line.
Can you touch on the difference between like absolute versus nominal?
Sure, yeah, that's a good point, and I think I get into this a little bit, I think, but no, it's great. So there are 2 types of filtration. There's nominal filtration and absolute filtration. The filter sheets that are used on the cellar side are considered nominal, which means that if it's rated at 0.45 micron, it's going to hold back almost everything that is greater than 0.45, but not all of it. There's a chance that some can get through because it is nominally rated. You can also, with pressure on those types of filters, get breakthrough. So if you get particles that are held up in that depth media and you build up your pressure enough, it's going to push it through. But depth filtration is going to be something like 80% of everything larger than that particle size is going to be held back, and 20% could get through. If you increase your pressures, it could be more than 20%. Absolute filtration is that everything that is 99.9999, right, 7 nines, everything that's larger than that micron rating is held back and not getting through. So that's another reason why there's a lot of redundancy in that filtration chain, because you're going to get some through on the nominal, and it's going to hit that final, which is absolute. That's the only part that is absolute, by the way, is that final filter. Everything upstream of that is usually nominal. Not always, but usually. So you don't want to hit that with a lot of particles that are greater than 0.45 micron, or you're going to start to plug really quickly. Does that make sense? Did I answer the question okay? There's 2 types of filters. We've talked a lot about depth media. Depth media is random structure. And this is what I mean by depth. Like, you get all these particles get trapped either through adsorption or through this matrix that it goes through in different parts of this thicker grade media. That's on your filter sheets that are on the back of the bottling line. Surface or membrane filtration is going to be just the surface. That's all you have. You don't have, because it's 0.1 millimeter thick, you don't have all of that depth to collect all of that junk, right? It's just sitting on the surface. So it becomes critical to make sure that you're loading the less expensive part of that filtration chain with more of the particles. And that when you get to the final, it goes through fairly easily, hopefully.
When you clean them, right, the filters.
Yeah.
And you have depth particles in there, what percentage is it actually getting the depth to clean those particles out of there?
So you're talking about on the filter sheets.
Mm-hmm.
On the filter sheets, I know you guys use a back flush or have used a back flush protocol. It doesn't get it out at
Okay.
all. The only thing that back flushing will do is release particles that are on the surface and push it back into the stream, which then come forward as soon as you change direction again. So
Which is moving around.
basically,
Yeah.
but that media is, if I remember correctly, something like 240, 250 millimeters thick. The particles that you're trapping in that media are like less than a micron. And so you've got this difference. They're not coming back out of that matrix unless you use like water or a solvent of some sort that can dissolve them. If you're just pushing back with wine, it might help you get through the last 100 gallons on a run or something like that, but it's not going to have an appreciable regeneration. I've talked to the seller side about that a lot. They still believe in back flushing, so
Yeah.
that they don't believe me in that.
Yeah.
The other thing that you do is in that back flushing method, the pore size is on the outlet side, right?
Okay.
As you back flush, you're putting a lot of pressure on that face of it, and that face is what's rated for that micron rating. So the more you back flush, the more that you degrade that paper, if you want to call it that, or that fiber,
Yeah.
And you start to have less control on your porosity. So
Kind of like
starts to
making
open it up.
holes in it.
It's more like if you think of the hole being triangular shaped,
Mhm.
it's not, because it's like this.
Yeah.
But if you think of that last little bit toward the outlet side being triangular shaped,
Yeah.
you're starting to wear it away and open it up.
Okay. And they do back flush, seller.
You didn't hear it from me, but that's my understanding.
Okay.
Yeah. Any filter sheet can be back flushed, but we don't recommend it for those reasons.
Yeah.
It doesn't accomplish much. It's a false sense of efficiency.
Yeah, the way you explain it makes sense. It doesn't seem like it doesn't.
That's during production, but during sanitation cycle, like cleaning it with water chemicals, it has a different
Are you talking bottling line or?
bottom line when you're going.
Yeah, so bottling line is a little different. We were talking about the filter sheets that are on the seller side
Okay.
just before coming into the pre-bottling tanks. On the membranes in those cans that you guys are responsible for on the bottling line, those are different. And yes, you do see some regeneration in your CIP and SIP process. Because you're using water, it's a mild dilution, so it will dissolve some things like proteins, not so much, a little bit. Color, you're rinsing some color out of there. Any of those colloids that are polyphenols. There's a lot of stuff that you can accomplish just with water, and I'm going to get to that in just a minute in the CIP stuff.
We're starting to use peracetic acid more.
Yep.
Is that gonna help us extend the life of
For
this
sure.
plant?
Yeah, peracetic is a stronger solvent, and particularly early on in its life cycle, it degrades fairly fast into water. So after a few days, it loses some of its potency, but initially you get a very good dissolution of those particles, which is very good. but probably more important is the lines themselves. If you're setting up on parasitic between the pre-bottling tanks and the cans, because you get biofilm that can build up in those. If you run a pig through them, you typically will see it pick up some gunk, and parasitic filled in those lines will help to reduce any of that biofilm that can catch up to you. And that biofilm, when you run wine through it, is just gonna pass on to those filters. Make sense?
So you recommend doing PAA all the way from the bottling tank to the filters?
If it's, yeah, I mean, that's sort of your, you know, what's possible and what's not, right? Your process may not be able to do that. But if as early as you can in that line is advisable, but PAA is going to be much better than just water. Yeah. Caustic is a possibility as well. Our membranes are caustic compatible. You could run them, you know, run caustic through it, no problem. I think you guys are using caustic, if I'm not mistaken.
I'm not 100% sure.
Every Friday after shutdown.
Yeah,
And you don't bypass?
No.
yeah.
And you do that on?
Every
That's-
Friday night,
Okay.
all lines.
All lines, okay.
It's a very dilute form of caustic. I think it's, I don't remember, like 2% or something like that, or 2.
It's less than, it's like 1.5%.
Yeah. Caustic is great on something like a changeover from a wine that has a flavoring added to it. A lot of those flavorings have like citrus oils and things, like citrus added to a wine. Those oils are hard to remove from those filters, and then you run another wine through and it picks up some of that flavor. Caustic is one of the better ways to eliminate that situation. But PAA is a great step. It really is. If you're setting up on PAA over any extended shutdown, it's positive.
And these filters are good to go for a couple days on PAA?
Yeah.
You're not gonna melt them or?
No. They're completely compatible.
Scaffolding is?
Yeah. So that the cage, we're gonna get into how it's made and stuff, and you can pass around these examples, but the way that these are made, they're made in 10-inch segments. The membrane itself is this pleated stuff here, and then it's just in what we call a cage. That cage is nice and robust and holds it all in place, so that when you're going through high temps and high pressures, it needs to withstand those so it doesn't move around a lot. This membrane is seated at the bottom and the top. That's an important part. If you have a lot of movement, you tend to see this come apart or become unseated. Yeah, I'll pass these around and you can kind of see how thin these membranes are and how they're made. So they're made in 10-inch segments, and then you have a top and a bottom, which is a bayonet point at the top, and a code 7 is the most common, but there are a couple of other types that you can get that seat in the base of those housings and hold them in place.
And the wine goes up and out?
It goes in
and
out through the middle, yeah. So you have the pleating process, you make the membrane, then you pleat it, that pleating kind of gets rolled into that round shape. It meets up or marries up with that cage or housing, and then you have electronic welds or thermal welds that are made to seal it all up, to make sure that it's that it has integrity. And then whatever cap or whatever length you're making in 10-inch increments, it could be a 10-inch, a 20-inch, a 30-inch, a 40-inch. The most common is 30. Code 7 means the bayonet, sorry, not the bayonet, but the locking tabs on the bottom that insert into the base, 2 O-rings and the locking tabs. The bayonet at the top helps to position it inside that can. There's usually a plate in the can that holds all 12 of them in place so they aren't knocking against each other in production. That's kind of it. There's a lot more here about, and I'll be happy to expand on this if anybody wants to know more, but manufacturing is kind of boring. But that's how they're all made. Pleating, these ultrasound welds become very important because you're talking about one flat piece of, let's call it paper, that's pleated, and you got to get that to bind or close. That's where we see integrity failures most often, is probably on that seam. We don't see them very often, but occasionally it does come up. So that's an important part of manufacturing. Each one has serial numbers attached to it. These have a QR code that you can scan and actually trace. This is your end caps, and actually thermal welding them together. These are some images from Millipore still in my slides. This is your bayonet on the tip on the front, and your code 7 end cap on the bottom.
And you guys make them still down in Fresno?
No,
Oh.
these are made in Germany.
Oh,
Yeah, we've never manufactured
Oh, yeah.
membranes.
Oh, okay.
Millipore did those in Minneapolis, I think.
okay.
Yeah. So here's your diagram. Sarah, your inlet comes in, it goes through the outside of the filter and then out through the middle. They're single open-ended with double O-ring seal. So when you're installing, it's best to spray the O-rings with alcohol or dip them in water before installation. It just gives a little bit of lubrication before sticking them in and turning them. They can probably be seated without use of alcohol or water, but it makes it a little bit easier, and it makes it less common for a rolled O-ring or something like that. You want to align the cartridge tabs with the slots in the housing sockets. Keep the filter vertical when seating it in the socket. Once inserted completely, turn 90 degrees to lock the tabs in place, and then the hold down plate and tie rod nut on top of the assembly. Different housings have different assemblies. Some have a spring mounted tie down plate that as you lower the housing, it kind of comes down with the housing. Some have just a plate that sits on top. That's probably more common. So once you put your 12 in, you kind of got to line up those bayonet tips to get it to seat, and then, but it's important to have that hold down plate in place. Some places don't use it at all, and you have more movement, particularly on your hot CIP cycles. You get heating of that cage. It gets softer and it starts to move. So any kind of pressure, they want to sway and move and bang into each other and stuff. So that hold down plate is actually fairly important. Then you want to close the dome, tighten the bolts first by hand and then with a wrench for an additional 3/4 of a turn. And you tighten in a star pattern to ensure uniform seal. That's another step that's commonly missed, is the star pattern. You want to try to go opposite to make sure that you're not just tightening down one side first and that other side stays loose.
What do you guys have in place when you do the manufacturing, just to ensure the quality of all your filters are good? You know what I mean? Because every manufacturing, nothing's 100%. Right?
For sure.
What do you guys have in place?
We've had a couple of problems here that we've had to deal with. I would say number one, the thing is not eliminating problems altogether. It's how you deal with problems. If I get a call and there is a problem, I'm usually here the next day if I can be. The second is, how do we make sure that we don't run into problems? All of our 10-inch segments are integrity tested before they're even assembled. And then the final 30-inch stick is tested for integrity before it even leaves the facility. So we test those essentially 3-4 times before it actually leaves the facility and comes to you guys. that is not to say that we don't run into problems. We ran into one on a 12-round housing that one filter out of 12 failed integrity right out of the box.
Yeah.
It's a pain, because the first step is to start to look on your side. Are all of the gaskets okay? Do we have a leak somewhere else? And you start doing that troubleshooting, and it takes you guys a lot of time to do that. And then ultimately you determine, okay, it's not the equipment, it's inside the can. And then we have to look at each individual filter and see, was it all 12? Was there, a reason for this, or was it a manufacturing error? Manufacturing errors do happen, unfortunately. But all I can do is get here and help do some of the testing, but that becomes a critical choice in who you choose as a manufacturer. We don't have very many of those.
Yeah.
It's very few and far between.
So I've heard people talk about masking sometimes, that if you have all 12 in there, you might still pass integrity,
Mm-hmm.
because you have 12,
Mm-hmm.
and so just,
Yeah,
what are
so-
your thoughts on that?
So there's a diffusion rate that is different for every manufacturer, and you want to know that diffusion rate. There's a calculation that you can make, which is diffusion rate times, I will get you that calculation. But basically, that gives you a calculation to what is your allowable pressure drop during a pressure hold integrity test. With 12 of them, you can have an allowable pressure drop that you're getting close to, right? So, and I'll explain pressure drop and integrity testing in just a few minutes, but getting close to that fail mark, but it didn't quite get there, right? That could indicate that you had 1 out of 12 that had a very small integrity issue, right? That it didn't have integrity, but it was small enough that it held pressure to a degree, right? To a degree that allowed it to pass. But in operation, and after going through 1, 2, 3 CIP cycles, that problem becomes bigger and you fail integrity very quickly. So I think that's what you're referring to as masking. So it passed integrity, but just barely.
Mm-hmm.
You don't know that it passed just barely unless you were watching it.
Right.
The computer says it passed integrity. There's only a pass-fail, right?
Mm-hmm.
The only way to eliminate that would be to tighten up your specs on that pressure drop. Part of that pressure drop calculation is knowing your entire volume of the can and all of the piping upstream to the isolation valve.
Math.
A lot of math. A lot of math, and a little bit of, and so the tighter that you get that spec, the better that you're gonna be. In reality, 99% of integrity failures, you're gonna see it not hold pressure at all. It's gonna just fall, right? So you start, it may not even reach the 1400 millibars that it needs to start the test because it's not holding pressure. So the masking, it can be a challenge, right? But that's a very, very infrequent situation, very infrequent. Because usually if you have an integrity failure, it's a massive integrity failure and it's pretty clear. So, speaking of integrity, this is differential pressure. Are you guys running to differential pressure max still, or yet?
No, I think we just run to 2 million gallons or something like that.
We've talked about that a lot.
We watch differential pressures, right? You guys
Yeah.
monitor the differential pressures, but you don't run until
Usually try to get about
failure.
1.6 million gallons out of them.
Okay, yeah, I think that's a pretty good benchmark. We've had some discussion on this, and I think we've increased that to maybe 2 million. Maybe it went from 1.6 to 2 million, I don't know.
As close as possible.
But technically speaking, you should be running these to their maximum life to get the most number of gallons through it before it reaches its maximum differential pressure. Differential pressure is your difference between the inlet side and the outlet side, okay? So you go inlet minus outlet, and you end up with a value that gives you your differential pressure. That differential pressure in this example would be 3. You can go up to like 40 probably in differential pressure. What we're measuring here, by the way, is you have wine coming in, you have wine going out, and that pressure of the wine coming in is going to meet the resistance of that filter inside the cans. As it starts to plug up, as it starts to get plugged with particles, that pressure is going to increase on the inlet side because that pump wants to keep feeding it. It doesn't want to go through that membrane, and the outlet side is just at a trickle, right? It's still filtering as long as you have integrity. There's no issue. You can keep filtering until you get to, I think it's 60 is about the maximum PSI before they say, you run the risk of blowing it out. So you don't want to go that high. But theoretically, you could run that can until it reaches that pressure and squeeze every drop that you get out of it. In reality, though, it's more convenient to know, okay, I've hit 1.6 million gallons through this 12-round housing. I know that my cost of filtration is really low, and I have a shift change, or I have a change in lot. And so now is a good time to make that change. But in reality, you could be running it probably more than what you are. And you want to continue to push that. So if it's 2 million today, maybe we can get to 2.4, maybe we can get to 2.5 before we start seeing, huge pressure increases. But that's something that has to be, monitored over time and then make that determination. Does it make sense to run it that long and end in the middle of a shift,
The differential pressure, like you said, right here is 3, and so is that good or bad or?
That's low.
It's low, so what would be high?
30,
30, okay,
40,
all right.
yeah. But if you look at your computers, you'll see, increase and then drop. It
Right.
typically looks like, this sort of thing, but it's staying pretty constant from when you put those new filters in to, let's say 1.5 million gallons, and then it starts to go like this.
Mm-hmm.
And that's when you start, like, you've plugged a lot of the surface of those filters, all of that square footage that you had and all those pleats and everything is starting to get plugged up, and it's only going to get worse. And so you can kind of make a determination when you start to see that regularly and historically, because it's not probably going to come back with a CIP.
Yeah.
The more we run, the more you'll see it start to trend up slowly.
Yeah.
So we monitor
And
that.
it typically will be, like this level, and then it creeps
Mhm.
up, and then you run a CIP and it'll drop back down, but it won't come all the way
Yeah,
back
and it
down.
just starts
And it
to
just kind of
down.
like goes like this, and it just kind of,
Yeah.
but once you get close to the end, it's like, it kind of takes off. And that can happen in a day
Yeah.
or 2 days.
Is it your inlet pressure that's gonna change, or is it the outlet?
Your inlet pressure is typically going to increase, yeah, because it's wanting to flow at that constant rate, and now your filter is creating resistance because it's starting to get plugged up. Yeah.
Do you have to change out both sets, or can you just change out your pre's at that point?
Theoretically, pre's are designed to fail before the finals. If you say that 100,000 gallons could get through a final, you probably need to take 30,000 gallons off of that on your pre's, but it's hard to say because it really depends on the wine and how many particles there are that are in that 0.6 and up range that are loading onto that pre-filter. Generally, it's ideal that you replace them both at the same time. Yeah.
That always makes more sense to me, but yeah.
You aren't typically measuring your differential pressure on your pre's. You're just measuring, all of your measurements are on your finals. Your differential pressure, your integrity test, all of that is just on your finals, not on your pre's. So those pre's, if they're not doing their job, are not gonna get to that 1.6 million or 2 million or whatever gallons through a 12-round housing. If you're passing too much through them, they're going to plug your final filters too quickly. So they kind of have to work in tandem, but those pre's may not be loading as much as you think, depending on how well the wine is prepared upstream.
We have changed pre-filters to avoid re-sterilizing the line. That way it gives a little less pressure on the finals.
Mm-hmm.
And then you kind of get a mismatch of a fresh pre-filters versus a million gallons of final filter.
I think that changing them out, like if you wanted to be by the book and you were changing your finals or your pre's when they're loaded up and changing your finals when they're loaded up, you would just be changing all the time. And you would have too much downtime, I think, to be practical. You might get more use out of the filter, but there's a balance somewhere there in terms of cost of the filter themselves and the downtime.
And the pre's and finals are the same price, right? Or
No.
Oh, they're not.
They're significantly different.
Oh, significant.
Pre's are probably half of finals, pretty close. Maybe not quite.
And that makes sense.
They're there as a sacrifice, really, to protect those
Yeah.
finals. They are ultimately there to protect the finals. That's the only reason they're there.
Does the guideline of the 30 to 40 differential pressure, does that apply to pad filters as well, or is there a different?
It's a different calculation, but yes, it does. So, yes, when you start increasing pressures into that 30-40 range, you start risking pushing through that rather soft depth media, those sheets, because higher pressures will just break through.
So you're more worried about the inlet pressure than the differential pressure?
Correct,
Okay.
yeah. But differential is also used on that side too. That was one of the things that I discovered here actually, was that they didn't have pressure gauges on the sheet filters out there, on the filter presses. I think that's been changed. But that should be monitored, because when you get to the end of a run, especially when you're running 0.2 micron or 0.4 micron, you can push things through if you get too high in pressure.
Yeah, I think we have the gauges now, but I think it's still a manual check versus, connecting it to ignition and getting it in the water.
Right.
Yeah.
I mean, I think that's ideal, right? Because if you push even a small number of those particles through, it changes everything. It changes your filterability and all of that stuff. Sanitation. Hot water is the most commonly used method to sanitize filters, housing, plumbing, and bottling lines. 180 degrees for 30 minutes or 20. Actually, you don't have to get to 180. You'd probably be sanitary at 160, 170.
It's like 165 is the low and 176 is the new standard.
Just taught me something. But yeah, and in reality, it's impossible to keep that temperature at 180 exactly. It's going to fluctuate. Yeah. So you want all of those surfaces to be hitting minimum of 170-ish, minimum.
176.
176 minimum, and hold it there for 20 minutes. That becomes critical when you're looking at water usage. And California is a lot more strict on, and probably getting more strict on water usage, to make sure that we're using as little water as we possibly can to accomplish what we need to accomplish. It needs to be softened and filtered water. We have this challenge a lot in most wineries are on well water, most large wineries are on well water. That well water has to be treated. If you get any sort of mineral deposits like hard water, any colloids or things like that in your water, that also builds up on your filter. So you want to make sure that that water is treated as well as it can be treated, is as clean as it possibly can be, within reason, of course, budgetary reasons usually. But dirty or hard water can plug up pre-filters and final filters. Once temperature is reached, low flow rates are important, and low pressures below 5 differential PSI is what you're shooting for. Lower is better. When you add temperature, you make that plastic, that cage, soft. When you make that cage soft, all of those areas that we talked about, welds and all that kind of stuff, start to see more pressure, more leverage, because it's moving around in that housing. So pressures, particularly combined with temperature, need to stay as low as possible. Speed is usually not your friend on a bottling line.
Yeah.
You want enough to keep up with a filler bowl, in general, but not a lot more.
Yeah.
Have you heard anything about silica in the water?
Silica is another, yeah. I mean, anything.
I don't know if that's hard water or.
Yeah, silica would be, I think, considered hard water. I don't really know either, because, well, sand, right? So
Yeah.
it's sand in your water. That's definitely particles that are going to be
So I
creating.
just think of magnesium and calcium.
Magnesium, calcium, all of those. It would be really beneficial and recommended and to monitor the well water to see what is in there. You probably have the lab equipment to do the analysis here, I imagine. I don't know, but water analysis, maybe not.
No.
I don't know.
Okay.
Like we send it out.
We have solutions for that. The CDR will do water analysis, but it's $30,000 machine and probably less than $10 in consumable. It adds up when you start sending out water samples on a regular basis to get them tested. They're a couple $100, and over time that adds up, and maybe it pays for itself, maybe it doesn't, but I'm not here to sell you a CDR. Anyway, you can see these are some of the problems that you end up with. Like in that lower left picture, you see soft particles, right? Those are like colloids and things that are just kind of gumming everything up. In the middle photo, you have hard particles like your magnesium and silica and different things like that that are going to be hard particles. Now, what you effectively have done is just removed all of that surface area. It's not a lot, but all of that surface area from that area of filtration. If you multiply that times thousands and millions, you end up losing a lot of surface area and not getting filtration through. And the far right there is just high pressure, high temperature.
How high is too high of a temperature?
I think probably I'm comfortable with 195
Okay.
Fahrenheit.
What if it's stuck in a loop at 185 degrees for a whole hour?
That's fine.
That's fine.
Yeah. Technically, on the membranes that we sell you guys, they are saying 180, right? And I've asked them, like, well, that's ridiculous. You can't keep a line at 180, exactly at 180, when you've got 11 lines and your hot water tank's over there and your line is over there. And so there's sort of this kind of conservative number that they want to protect themselves as far as like 180 goes. But we're running on another winery across the valley at 212 and not having problems. Now, could you maybe get more throughput if you brought that down to say 195, 192? I think that the important thing is to understand, like, if I'm going from point A to point B, how much temperature drop do I have in getting there versus the first line? The closest line is obviously going to get hotter, and then set your hot water tank to try to hit a reasonable window that is as low as you can, but still reach that target of 175, 176 minimum, right?
Mhm.
So the winery you're talking about, 212 is what they're running it at?
Yeah, they're seeing 212.
All their lines? Or is it just the closest one?
It fluctuates a lot. They have a lot of lines, and 212 is, you know,
And the filters are holding up?
yeah.
Wow, okay.
I wouldn't recommend it.
No.
Like,
I'm just
it's not my
surprising.
recommendation, but the cages on these are pretty robust, and that's one of the things that we tested pretty thoroughly.
And then you can also do steam, right?
You can use steam, but with steam, pressures become even more important. You gotta keep that pressure low on steam because you're getting into really high temps. Yeah, but you can't. I don't think it's a good idea. I wouldn't recommend steam. The best cleaning method would be to stay in ambient for as long as reasonable, but 20 minutes, and then ramp up to your 190, let's say. The reason for that is that proteins will bake on a surface at 132 degrees. So you want to stay below 132 degrees as long as you can to make sure you dissolve those proteins before exceeding it. Because if you bake those proteins on there, they don't get off. So also in changes from red to white, you want to try to stay in that ambient temperature range longer to dissolve the color more. Cooler temperatures, ambient, is better, more effective at removal of color than your hot temperatures are.
What's ambient to you?
It would be.
I mean, 60.
60.
Oh, okay. I mean,
I
because
was
our,
thinking 97. I don't know why.
we do warm water, we do cool and then warm for, I think.
I think I'm just getting confused because that's what
90's
our
fine
temperature
too.
is, like a human, so when you say
Oh.
ambient, I'm just thinking, I don't know, that was a stupid thought.
Yeah. No, it's not.
That's why I asked.
It's just like, if you, to me, ambient is if you left a container of water out here, it would be at, you know, like
70
70 degrees,
Yeah.
something like that. So 60 to 70. To me, that's ambient. But below 130 is the critical part. You don't want to hit it with 130 quickly, which from what I've seen, you guys line can't really do that anyway. So. Integrity testing, all right. You're only integrity testing the final filters, not the pre-filters. And this is our test to make sure that we are holding back all of those yeast cells and bacteria cells, right? So this assures your filter retention and bottled product quality. You're detecting issues from improper filter installation, damaged O-rings or other gasket seals, damaged filters from excessive pressure drop, differential pressure during hot CIP on plugged filters, or chemical non-compatibility. So anything that this filter has seen that could possibly have caused it an integrity loss is tested at that point. When you go and install 12 filters into a can and you put that housing over the top and you run an integrity test, you don't have visibility of it anymore. You can't see it anymore. You can't say it's that one or it's that one. And so you got to make sure that you follow your procedures in seating all of those correctly, making sure that they're all installed right. And then we're going to test it to make sure that it has integrity and is going to do what it's designed to do. You want to do integrity tests at installation, so new or after long-term storage. So after every chemical or sanitation procedure and after every bottling run. Basically, you want to integrity test any opportunity that you can that makes sense. So anytime that you're starting up, anytime that you're running a CIP, anytime that you're installing new, or some that have been stored, you're gonna run integrity test pretty much all the time.
I have a question about the storing. Like,
Mhm.
how long can you store? Like, when you're saying storing, you mean not that I paid for a pallet and stored for a year? Are we saying like I used it once and then stored it? Is that what you're
Yeah.
saying? Like, what? How long is the shelf life after I've used it? I don't know. Say for a week and then I wanted to store it.
So there's two different methodologies for storage, or three, I guess. One would be a citric adjusted pH down to 3.5 and SO2 at like 300 to 500 ppm, and in a closed system. So a lot of small wineries, if they buy a 30-inch stick and they're filtering 500 gallons, they've used only a small portion of that.
Yeah.
They usually will buy like a PVC pipe with a cap, and they'll submerge it and use one of these methods. The citric adjusted SO2 water is one. The downside is it has to be continually monitored, and that's usually monitored and changed every couple of days to a week, so you gotta maintain that water.
Because of bacteria, right? Yeah.
Yeah, you can get
Bacteria
mold and
mold.
bacteria and all that kind of stuff. The other method, which I prefer, would be ethanol storage. So as long as it's, 80 proof, or is it 80 proof or 80%? I'd have to look. But it's pretty high on the alcohol,
I think it's 70%, 80 proof.
something like that.
Something that it's.
And again, submerged, right? Because if you have anything that's above it and getting air to it, it can grow mold and things like that. The main thing that has to be monitored there is to top off your ethanol to make sure that it's staying submerged. But in that method, in either of those methods, assuming those conditions, they can last a long time, a year probably. I would recommend in both cases, remove the O-rings. That's also another recommendation that I have. If you're pulling out, a plugged membrane, they're done, whatever. Pull off some of those membranes, or those O-rings, and keep them on hand, just so that you have extra O-rings in case you lose one, in case it didn't ship with one, in case, I don't know, you've got a crack or something. It's always good to have those sort of on hand. And you don't want those O-rings in that solution stored for long term, because that will degrade the O-ring itself. But the filter itself is fine.
Jerry, I got a question. You know how we have that little extra housing?
Portable?
Yeah, do we store those filters?
Yeah.
We do? What do we use?
I want to say it's the
ethanol?
citric,
Oh, the citric.
tablets.
Alright. I
Yeah.
didn't know that.
I know that in some cases, like we had that one issue with integrity on a 112 round, one membrane out of 12. Those other 12 were stored temporarily before they could be put into a line. My recommendation with you guys would be to get them in use as quickly as possible and not store them. Just put them in your next opportunity and get them back in operation. Storing is, it's a good method, but it's a little less reliable.
Yeah, for sure.
Maybe do PAA too.
Sure, but PAA does degrade quickly, so it's gotta be but it degrades to water, so you should be fine if you're in a closed system and it's truly closed to no oxygen, you should be good for a period of time, but I think I'd wanna do a little bit of testing to see how long it would be good for.
He just brought something of that, maybe question. So he's saying we use the citrus message, citrus tablet. Is that something you sold us for that?
No.
Or? No. Okay. No.
Who knows how we get them.
Yeah, that's what I'm thinking.
We have a lot of citric acid.
Oh, we do.
Yeah, a lot of citric acid and a lot of SO2 if you need it, I'm sure.
Is it okay to do it without the SO2?
Yeah, it's less desirable and for shorter periods. But with you guys, I imagine you're not sitting around on those stored filters for very long.
No. I just.
I would try to target a week or less, if at all possible.
I think that's for our single round housing that we
Yeah.
have, that we'll put in line on occasion, that's how we're storing that one.
Yeah.
We put a pre-filter, right? Put it before the pre-filter.
Got it. Yeah.
If
For
we
when
have
we
a-
have those
a-
filter
Oh, right, yeah,
issues.
Yeah, when we have filtration issues, we put it
Got
in line.
filterability issues, you put in this is
Single round.
dual pleated,
Well, extra
Yeah.
12 filters,
what's that?
extra 12 filter housing.
Oh, sorry, it's a
Oh,
12
it's a
filter
12,
housing.
okay.
Oh, and so we store it on
Yeah.
Citric when we're not using it,
Yeah.
which is a lot,
Hmm. I would just check it, monitor
okay.
it.
Check it.
It's not gonna create any issues, cause you're still gonna go through an SIP.
Yeah.
So, you're gonna get it clean again, but are you losing some surface area? Maybe. Integrity testing principles, so this is a non-destructive test that
I have one
measures.
more question.
Yeah,
What about just over the weekends? Cause I think we lay up on water now, to keep
I
it
think
wet.
PAA would probably be better, but water's fine. Yeah, if it's clean water, yeah. Or you can pressurize with about 14 PSI of nitrogen.
Oh, just for over the weekend.
That's good for a couple days. As long as you have that 14 PSI maintained. So integrity testing, it's a non-destructive test measuring passage of gas under controlled conditions through a wetted membrane, and there's two types, bubble point and pressure hold. So the easiest way to explain integrity testing, those membranes have very small holes in them that allow the passage of wine through and holds particles back. When you're wetting that membrane, you wet it and then drain it. There's still moisture or water in that membrane that's held up. It's surface tension, right? So that surface tension bridges the gap between those holes. Then you apply gas. And you're measuring for bubble point, the point at which the gas breaks that bridge between that 0.45 gap in that membrane. So you have water, you're pushing gas, it's actually the other way, pushing gas, and when that gas breaks that surface tension, that is your bubble point, okay? Bubble point is good for 1 to 3 round housings. It's not as reliable for a 12 round or a 24 round. So all of your skids are designed to use pressure hold. Pressure hold means that you take it to 80% of what the bubble point should be, and you hold it there. And then you watch for that pressure decay. That pressure decay is allowable up to a certain time and value. So over 5 minutes, you might be able to drop, I don't know, a few PSI. And in that time, you might see it go down a little bit, but as long as it holds in that 5 minute period of time to a certain value, you're good to go. Make sense?
And it does that in the little computer thing that we have.
Yeah, it does that automatically, so it'll take it up to like 1400 millibar, and then your timer starts down, and it starts counting down, and it's watching that pressure decay, and you can see it kind of move up and move down in those values. Usually, an operator knows almost immediately if it's going to hold pressure or not, because you'll start to see it tick down in big chunks, like 10 PSI, or 10 millibar, 10 millibar, 10 millibar, and over the course of 5 minutes, you've just lost 500 millibar. If you start to see that, you can probably reliably say this is gonna fail integrity and start your process of looking for, you know, where could this have been on our side, on the equipment side. And then if it fails again, then call me. I'll come and try to figure it out. This gets into a lot more detail on bubble point. So this is measuring the pressure at which the liquid wetting the membrane is extruded out, or that the surface tension in that membrane is lost. And so the gas starts to bubble. That's usually done through a tube. You guys, it's good to know bubble point, but you guys won't be using it much here because it's all done automatically on your skids. But this is the principle that's used. And it's the same principle used on pressure hold. It's just not reaching bubble point, and it needs to hold that integrity, right? So that it doesn't. If you had a larger pore size, your bubble point would be a lower value. If you had a tighter pore size, it would be a higher value. So every manufacturer has its own criteria for what that bubble point is. I just kind of explained that. So on a 0.45, you're greater than or equal to 26 PSI. So if I start applying gas at 5 PSI increments and stabilizing, 5 PSI and stabilizing, 5 PSI, as soon as I get to 26 PSI, I don't need to go any further. I can say that it has integrity. If it goes to 32, great. If it goes to 35, great. If it goes to 27, great. It's still integrity, right? It still has integrity. And it's different for a 0.2, it would be 44 PSI. So it has to take a lot more pressure to break that surface tension on a 0.2 micron. The steps of bubble point: you wet the membrane, shut off the line pressure after filling or wetting, close upstream isolation valve and downstream isolation valve, open both housings, drain and dome vent, and vent the dome. Water will drain from both upstream and downstream sides. Then you apply some sort of a gas. It could be air, usually it's nitrogen. You apply it either to the dome vent, the dome pressure gauge port, the upstream pressure gauge port, and you set your regulator to 10 PSI. Then you attach a hose to the downstream drain valve over here on the downstream side, and you submerge that hose in a bucket. So as you increase the pressure in increments of 5 PSI, allowing it to stabilize, some water will start to form. You'll see some bubbling, but it won't be like a boil. When you do reach bubble point, it starts to look like a boil. And that's when the gas has actually broken that seal on that membrane and passed through that hose into that bucket and starts bubbling. Small bubbles may occur due to diffusion. So there is a diffusion rate on these that's allowable, meaning that there is some air that's trapped in there that gets pushed out. Vigorous bubbles is what you're looking for on bubble point. And I wish I had a bubble point with me. The R&D team was using our single round housing. If you get bubbles appearing prior to reaching bubble point, it indicates a potential failure. So you should check your setup and run it one more time, just like you would on your skids.
That's what we usually do when the finals fail and we don't know which filter it is, so we do that on the single housing.
Yeah. I was talking to Richard about some of that. One of the things that you can do is use a garbage can filled with water. And the easiest method is actually called reverse bubble point, where you take like something like a bung and put you need to seal it up, but you're putting a gas supply into the code 7 end and increasing that gradually underwater in a trash can. That then would indicate very quickly where that problem is. So it's a lot quicker. You just dunk them and apply that gas, but you need like a bung or something that's sealed.
Instead of the single housing, takes a couple minutes each one.
Yeah, and then you add that up. It takes a lot. I've done it a few times. Pressure hold. So you're taking it up to 80% of the known bubble point, right? So 80% of that 26 value. It ends up being like right around 20, 21, something like that. You take it up to that and hold it. And if the pressure drops too fast, 2 PSI in 5 minutes, the filter failed this gross integrity test and troubleshooting should occur. That's what you guys do on the skid. That's what's automated on the skid. It takes that pressure up and holds it. The one thing that can be problematic is you're reliant on the gauges. So you're only as good as your gauge is on these and how often they're calibrated. Precise pressure gauges. Troubleshooting, loss of pressure due to hardware leak, housing, upstream piping, any gaskets or clamps that have fittings, all that stuff should be checked. I'm sure you have spray bottles with soap in them, so you pressurize it a little bit and spray it down with a little bit of soapy water. You can typically find a leak fairly easily. A lot of times it's just a gasket, sometimes it's a valve, but it takes a lot of work on some of these lines to try to follow all of it and figure out where all of those possible leaks could be occurring. You want to check your dome to base housing gasket condition. You should do that every time you open up a can to make sure that gasket on the bottom is intact and has integrity. No cracks, flat areas, nicks or abrasion, no quote unquote homemade gaskets. Threaded connections, reseal with Teflon tape. Valves, replace valve seat or the valve itself if necessary. Avoid Teflon gaskets. EPDM and silicone are better in these applications. Most of those are going to be EPDM on the line. Silicone inside the cans typically. Troubleshooting upstream to downstream leak. Filters not fully wetted. Almost always the cause of this type of problem. So if you wet the membrane and you perform pressure hold, but you didn't effectively wet the entire membrane, there's no surface tension of water in that portion that didn't get wet, and so gas will pass through immediately. Re-wet using a previously described procedure. O-rings might be rolled or damaged during installation. This is one I had just the other day. I was installing some cartridges on a 24 round housing, and I was opening up the filters and the operator was grabbing them from the plastic sleeve, and I held on to one of those plastic sleeves a little too tight and rolled one of the O-rings off of the bottom of the membrane. And we installed all 24, put the can back on, and failed integrity, had to take it all off. And,
That's happened to me.
And then try to find the one that was missing the O-ring.
Yeah, inside the bag.
Yep. Filters, O-rings rolled or damaged during installation. Inspect the O-rings. Housing, internal O-rings are missing or damaged. Filters not integral. Contact me, and I'll help you troubleshoot as best I can, as quickly as I can. If you do run into a problem, I just ask that you guys save the filters and try to bag them. It's harder to do an autopsy on a filter if it's been wetted or you've seen wine and then left exposed to air, because you get mold exposure, and it's hard to get through all of that growth to get to the root of the problem. So if you do run into a problem, hold on to them for me and we'll try to do an autopsy to see what went wrong. Shut down and short-term storage, we've already covered this, but you want to push wine from the housing with nitrogen, flush with ambient temperature water in a forward direction. Probably integrity test at the end of those. Again, we're testing integrity all the time, right? Warm water regeneration cycle followed by a sanitation cycle. Close up the valves, pressurize the housing with filtered nitrogen. System is good for overnight to a weekend. So that's your nitrogen method. If you're setting up on PAA, it's probably even more effective for that couple days, right? Long-term storage, most frequently cartridges are removed from the housings. O-rings are typically removed, stored in a solution of SO2, 300 to 500 ppm, and citric acid adjusted to water to 3.5 pH, or submerged in 80% ethanol. We already covered that, right? And that is the end of my presentation. I think I think I'm on time.
You are on.
Okay.